Okay, so we're going to look at some group theory today, and we're going to look at isomorphic groups. Now, we're going to use these rules here and some of these comments here, like this, to find out if two groups are isomorphic to each other or not. Now, the two groups I've picked here are the coprime integers of 18 under multiplication modulus 18, so that's the group action, and that's the group. And then this group here is the integers from 1 to 6 under multiplication modulus 7. So these are different moduluses and completely different groups. And some members of this group will not be in this group. But that's okay when we're looking for isomorphic groups, because we're looking for one group that can map all its elements onto the other group while still keeping the form of the group. Now, both of these groups are both cyclic. So cyclic to cyclic in isomorphisms, that's always a good place to start. So that's probably one of the most important things for what we're going to show today. Now, order of groups for any isomorphism, they have to be equal. So they have to be the same amount of elements in this one as there is in this one before we can progress. So I'm going to call this group A and this one group B. So let's have a look first what group A is. So all the elements will be coprime integers of 18. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 is good, 14, 15, 16, 17. So group A has order 6. So let's have a look at group B. So group B is just simply the integers from 1 to 6. So this one has also order 6. So the order of the groups is equal. Now we want to find out and show the order of each element and see if we can find its generators. So we'll start with this group first. So we'll find what group 1 generates, what group the element 1 generates. Well, 1 in multiplication is always the identity. So 1 will only reproduce 1 itself every time. What about 5? So what we're looking for here is 5 to the 0, 5 to the 1, 5 to the 2, 5 to the 3, and 5 to the power of 4. And that will generate, hopefully, the whole group, or give us an order of a subgroup. That's what we're interested in at this stage. So 5 to the 0, that gives us 1. 5 to the 1, that gives us 5. So that's easy enough. 5 squared is 25. 25 modulus 18 will give us 7. So now we can use this one. Instead of doing 5 cubed, we can just take this one and then multiply it by 5 to give us our next element. So 7 5s are 35. Modulus 18, that will give us 17. Multiply this by 5, we get 85. And then modulus 18, that will give us our 13. And then 13 5s are 65. Modulus 18, that gives us our 11. So 5 is a generator of that whole group. Let's have a look at number 7. So now instead of using the 5 here, we just change the 5 for a 7. So 7 to the 0 is 1, 7 to the 1 is 7. Now what we do now is multiply each one of these by 7. So 7 7s are 49. So that then gives us 13 modulus 18. 13 times 7 is 91. 91 modulus 18 gives us 1. So we're back to this one. Now, as these groups are of order 6, so order 6, if we take the factors of 6, that should give us the order of all our subgroups. So factors of 6 will give us 1, 2, 3, and 6. So we should find groups of subgroups of that order. So now let's have a look at number 11. So again, replace 5 with the 11 here, so we just end up with 1 and 11 to start with. 11 times 11 is 121, modulus 18, that's going to give us 13. 13 times 11 is 143, modulus 18, that's going to give us 17. 17 times 11 is 187, modulus 18, well that's just going to leave us with 7. And then 7 11s are 77, and hopefully that will leave us with 5. And that does. So 11 and 5 are generators. I'll just put a little G here just to signify that these two are generators. Now we try 13. And if our sums are right, we should get one of 13 or 17 being a subgroup of order 2. So we've got a 1, a 6, a 6 and a 3. There should be a 2 in here somewhere. So 13, again replace these 5s with 13. So we get a 1 and a 13. 13 13s are 169. Modulus 18, that gives us a 7. 7 13s are 91. 91 modulus 18 generates us back to 1. So this one is of order 3. So now we're left with 17. So hopefully this gives us our group of order 2. So change the 5 for 17 in our calculation. So we end up with 1 and 17. 17 times 17 is 289. Now modulus 18, I know 16 18s are 288. So that gives us our 1. So this then gives us our group of order 2. So that's all our subgroups for the first one, coprime integers of 18. Now let's have a look at B and see if we can find our subgroups of this one. So again, 1 under multiplication modulus 7. So 1 is only going to generate the identity element. Then we're going to look at 2. So 2, so again we follow 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4 and so on, and see what we can generate in this one. So 2 to the 0 is 1, 2 to the power of 1 is 2. Now 2 squared, so 2 times 2 is 4. 4 2s are 8, mod 7 is 1. So that's an order 3. Okay, number 3. So again, always start off with 1 and 3, that's our powers of 0 and 1. 3 3s are 9, mod 7 is 2. 2 3s are 6. 6 3s are 18, mod 7 gives us 4. And then this should give us a 5. 4 3s are 12, mod 7 gives us 5. So 3 is a generator. Let's try 4. Okay, again, start off with 1 and 4. 4 4s are 16, mod 7 is 2. 2 4s are 8, mod 7 is 1. So here's a group here of order 3. So 2 and 4 are both of order 3. Let's have a look at 5. Okay, again 1 and 5 we put down first. 5 5s are 25, mod 7 gives us 4. 5 4s are 20, mod 7 gives us 6. So we're looking like this is going to give us a generator. 6 5s are 30, gives us 2. And then 2 5s are 10, which gives us 3. So 5 is also a generator. Now we'll look at 6. So start off with 1 and 6. 6 6s are 36, mod 7 is 1. So that's our subgroup of order 2 taken care of. So that's all our subgroups. So now what we're going to do to find our isomorphism, so what we do is we write it down something like this. So if we take phi to be, we can write this, the group with its order and its operator, will give us a mapping of this group. Now we could have just written the A and the B because we've already specified that subgroup, but I'm just going to write it down like this for now. Okay, so I'm going to write down the group mappings from here. So we can use 5, will probably map to 3, or the 5 in this group. So let's have a look. First of all, first place to start off is A to the 0 and B to the 0. So if we pick a generator here, pick this one. So let's use, just put a note here, generator 5. 1 is what we have on this side of the group. So if we're going to map it with this one, so our mapping here is with 3, we're going to map each one of these with each one of these according to the powers. So using this little table here. So 1 will map to the 1. 5 maps to 3. 7 will map to 2. 17 will map to 6. 13 will map to 4. And 11 will map to 5. Now that is one isomorphism we can do there. So we can call this isomorphism 1. Now because we've got 2 generators, we could probably produce 2 isomorphic mappings as we've done here. So let's try another one. So we've done 5 and 3. Let's try 11 mapping onto 3. Let's see what happens there. So we'll call this one phi of 2. And we'll just go A to B on this one. Let's just call it that one. So we're going to use this group, this subgroup here. So 1. So identity always matches to identity. So we'll use this one here. 11 and 3. 11 maps to 3. 13 maps to 2. 17 maps to 6. 7 maps to 4. And 5 maps to 5. That's another isomorphic mapping between the 2 groups. So if you draw up a Cayley table for this group and this group, and then mapped up each element on the other one, giving it a colour, you'd find the pattern of the Cayley table will be retained after the isomorphism. So I'm going to leave that for you to have a go at that yourself and see if you can find any more isomorphic mappings within these 2 groups. Okay.